Hello, everybody. Thank you for letting me the opportunity to be there. So I'm actually the co-founder of Hydric Engineers, SME located in Switzerland, and presenting this topic on behalf of Veolia because it's it's the very important partner we have working in France, especially in the wastewater sector, and of course we also plan to work on other countries on that. So we had the chance to see very big pipes and a lot of new projects. What I will present will be on the operating side of wastewater and water evacuation. So no big new constructions, but we really help using the existing ones at the optimal level. So you have heard a few times this morning and maybe yesterday the word digital twins, and it's sort of a new word, but if we apply the definition, because digital twins are very often compared to just models. Of course there are models behind them, but the specificity of being a digital twin is that the model is a replicate of the reality, so this is a model, but the model must be connected to the prototype, and it must be connected live, so meaning in real time. And additionally, it must be connected bidirectionally, so the twins have to get the information from the infrastructure, but it has also to control directly the infrastructure. So a few just more detailed explanations. So here you can see on the bottom of the image the sensors which are placed on the infrastructure, so typically measuring sewer discharge, water height, height of some reservoirs. Then this data flows directly to the SCADA of the operator and can be accessed by the operator. This is in general done on the treatment plant, or it's centralized in the plant. Then this SCADA can be connected to another system, which will be the digital twin or the model. So in this case, the data from the SCADA is exported into the cloud, and in this you have the databases, the models, you get some other data, not only the data from the prototype, but also external data. Typically, weather forecasts are part of the important external data you use then to take decisions. And the twin can be also accessed by all users. So we represent the dynamic processes of the real system, and we are connected from the twin directly to the system to provide informations. A few details on the model. So we are working for twins in the wastewater evacuation sector. So we are focusing on the sewer system, and we will model the catchment area. So modeling the natural flow coming from the watershed, also the pollutants, typically sediments and fine particles. Then we will model in a very classical way of a rainfall runoff simulation the urban hydrology, so runoff water, infiltrated water, wastewater, including also the polluting fraction, wastewater, parasite water, infiltrated, ammonium, and then we can also model in the same the final concentrations in the natural environment, so in the river or in the lakes. And this model runs in real time, runs live. So every 10 minutes you have new runs, new information, everything is updated. This is the principle. Here just a zoom on the city modeling. So of course you have to take into account the catchment area, the impervious area typically, the infiltrated one, then chambers, sewers, other infrastructure such as reservoirs, and then you connect the whole to the river. Very important data is the weather forecast, and it exists a lot of models for this, a lot of providers, and you have to play with all of these ones. No one is always better than the other, and it's a hard work to select the best case for a given event. In the case of urban hydrology, radar data is important, and what we use is not only the current radar information, radar measuring precipitation, but we also use radar forecasts. This means the information that you see here, which is the precipitation given now, will be advected using other numerical weather model information, typically wind fields. The cloud will be advected, and this will give you a prevision, a forecast of the rainfall over 10, 20, 30 minutes, up to 6 hours. And this moved or advected cloud will be blended into the numerical weather forecast. So there are different systems. In Switzerland, it is called INCA. So now I will show you the real application of this theory on the example of Saint-Chamond. Saint-Chamond, it's near Saint-Étienne. Maybe you've heard that name for the soccer team, which used to be good when I was a child. It's in the center, and it's about 40,000 inhabitants in the case of Saint-Chamond. The situation is very interesting. The wastewater treatment plant is located there, northeast. So the flow from the catchments goes from southwest to northeast. And on the upstream part of the catchment, there is the sewer system is managed by another company. In that case, it is Suez. And the combined flow reaches a stormwater reservoir called Terre Noire. And this reservoir, number 2, has a regulated valve. And if this reservoir is spilling, then the wasted or polluted water would flow into the blue lines, into the blue river, which is called the Gier. So we have to try to minimize the overtoppings of this reservoir, but it's not easy because downstream of the system, along the sewer system, we have combined sewer overflows, which are not controlled. And if too much water flows into the pipe, then you would have wastewater releases also into the Gier. At the end, we reach the treatment plant, having also a combined sewer overflow, and this treatment plant has also a particularity. It is that there are 2 processes. One process is for dry water, dry situation, and the other process is for rainwater situation. So a second line. I will come later on it. So our 2 problems in that case. So the first case is to try to operate optimally the wastewater treatment plant. This means we have to be able to engage, to activate the rain process of the treatment plant in advance. So before the water is effectively flowing into the system. And the response time of the catchment being between 10 and 40 minutes, we have to be able optimally to activate it 40 minutes before. So we absolutely need a forecast. We cannot just rely on monitoring systems or pluviometers in real time. We really need to have additional information if we want to be able to do that. And if we can do that, of course, we improve the treatment efficiency. So that's the goal. And the second objective is to optimize the total sum of spillings from the sewer system, meaning we have to reduce the sum of spillings from the retention reservoir, the combined overflows, and the entrance of the treatment plant. So it's a global optimization to do, and you will see also some details on it. So a first look into the first forecasting phase. So the system is a Denzadeg, which, of course, as I said before, this system likes to be activated before the water comes, and we will try to make it. And the role of the twin is in that case. So the twin receives some information from the network. We model the flow. Then we get the precipitation forecast. We simulate and we predict the flow over the next few minutes. Based on this, if we reach some thresholds, then we will automatically activate the DensaDeg to open it. Practically, it looks like this. So on the upper left, you see the platform of the digital twin. So here you have all the information you need. What you can see here, for example, you see some different colors, meaning that we predict an overtopping of this combined overflow. We predict an overtopping at the treatment plant. We can get the discharge, we can get the precipitation forecast, the observed precipitation, etc. So all this digital information can be accessed on the web platform. And the most important information for the operator is directly transmitted to the supervision. So he can, without changing the system, can having a look on the inflow prediction. And based on this, the SCADA will automatically activate the process. Here you see into more detail an example of a situation. On the higher chart, we see the inflow and the inflow forecast. And on the lower chart, we see the activation signals. And of course, we have to develop the algorithm that help us to have the best performance, meaning that it's about prediction, so we make errors and we try to reduce the risk of these errors, of course. So in that case, we are maybe 10 minutes before 15. This was an event a few weeks ago. We would predict according to two models. One would say, oh, not a lot of water is coming. The second one, which is based on radar, says, oh, we will go over the threshold, so we might need to activate the DensaDeg. This is confirmed by the signal, who says continuously activate it. If you zoom here, you can see that 10 before 3, we ask for activating it, but the threshold actually is passed 10 or 20 minutes later. And on this example, it's still better. So there is 30 minutes delay between the activation and the effective entrance of the real discharge. So in that case, we were able to activate the system 10 minutes before the flow is coming, and in that, a few hours later, about 30 minutes before. This is more an example of how we develop these systems, because in theory it's easy, we just need to predict, but as I said before, there are very high uncertainties, and you have to find a real compromise between what we call probability of detection, which would be 1. This means that every time a flood is coming, I was able to predict it. And in the contrary, we have the false alarm ratio. So every time I predict a flood, does it come or not? And for Veolia, the problem is to have higher false alarm rates. Over 10%, they would not automatize the system. They would not rely on the prediction. And at the very beginning, we had a system which was producing a very good probability of detection, over 60%, but almost 30% of alarm risk. So this was too much. And then we could optimize the system and find an algorithm providing about 50% of probability of detection. So one event on 2, we are able to activate the DensaDeg before the water is coming, and only one prediction on 10, it's a mistake. And we are, of course, looking for this optimal zone of the Pareto curve, so trying to reach 1 for probability of detection and less than 0.1 for false alarm rate. So this was for the first use case. The second use case, as I explained before, is the goal of limiting the overall spillings of wastewater into the environment. And for this, we use simulation optimization with the digital twin. So how does it work? We get the information, the prediction information from this external information, so a radar forecast. We use the simulation model to convert this precipitation into flow in the sewer system everywhere in the catchment, so upstream of the basin, in the middle, in the storm overflows, and in the treatment plant. Based on this information, we run optimization systems which will help us to take the best decision. How much should we open the valve, even if the rain is still not there? But we can adjust this, and then we take the decision. We wait a few minutes. During these minutes, the real flow happens, and we initialize the system again because we have a new real water level of the reservoir, new inflow, new situation in the system, and we can then take the next forecast and the next optimization. In the case of Saint-Chamond, we have the chance to be able to use a rule-based, what we call rule-based control. This means we can develop rules which take into account the predictive information, and we don't need necessarily to make the full optimization process. So after 2 years of experience, we can see that the system has a very positive influence on the catchment area. Before our developments, we could say that in average over 1 year, the total spilled wastewater was about 200,000 cubic meters per year. This was based on passive regulation, meaning some simple rules like if the reservoir level is increasing, then I would close the valve. Or if my pluviometer measures a precipitation, I would close the valve. No predictive information in the system. If we introduce predictive information in the system, we could reduce by 44% the total volume of pollutants into the environment. That would be with perfect forecast, if we know the future. But we don't know the future, we try to guess it. So the REAL-T showed that we could, in fact, reduce by almost 30% the total emissions of the system using the real forecast, and this is just based on the archives of what we provided. So that's the real results that we could get out of the system after 2 years. So to finish, about these two use cases. So first, predicting flow in the treatment plant is not easy. It's possible. For the moment, we are at a 50% success rate to activate it before, not too many false alarms. And the best proof that it's working is that the operator effectively uses it. So it's automatic since 2 years, for 2 years, and it's accepted, and it works like this. On the second hand, the dynamic regulations also prove to work with a real reduction of the emissions by almost 30%. It's also an automated process, and we just need sometimes to check it, recalibrate it a little bit, because every event we have new information, and the system can learn from this new information. And this year we are developing with Veolia 5 new projects in France. Some are a bit more complex than the one of Saint-Chamond, and all these projects are based on these two main components: predicting inflow in the treatment plant and optimizing the reservoir for the sewer system. That's it. Thank you very much for your attention.